So for today, we will discuss about deductive reasoning and also the law of detachment and syllogism. Okay. Okay. Let's hear this.
So a little review, we learned inductive reasoning, which is to use patterns to make a conjecture or a prediction. Today, we're learning deductive reasoning, and deductive reasoning doesn't use patterns, but it uses logic from given statements or facts to make a conjecture. So difference between the two, inductive reasoning uses a series of patterns, deductive reasoning uses logic and fact. Within deductive reasoning, we have two laws. We have the law of detachment and the law of syllogism. So first, let's talk about law of detachment. We have the law of detachment states that if the hypothesis of a true conditional statement is true, then the conclusion is true. So symbolically, what that means is I have to be given a conditional statement, P then Q, if P then Q, that's true. It has to be a true statement. And I have to know that P is true, or that P is given. If I have those things, then, and these three little dots mean therefore or then, I can conclude that Q is true. So symbolically, there's the law of detachment for us. Let's look at a couple examples. So the first one says, if there is lightning, then it is not safe to go outside. Johnny sees lightning out his window. So what we want to do is we want to break that first conditional statement into the hypothesis and the conclusion. So here, this is going to be my hypothesis. There is lightning, and I'm going to put a P underneath that. And then our conclusion is that it's not safe to go outside, so that would be my Q. So I have, symbolically, I have a statement that says P, then Q. Now I'm also given another piece of information. I'm given that Johnny sees lightning out his window. Now if we look, it's not the exact wording as the hypothesis, but it's the same information. The hypothesis is there is lightning. Johnny sees lightning, so there is lightning. So that counts for saying that P is true. So I know that P then Q and P is true, so I can conclude Q. I don't want to conclude a whole statement, I just want to conclude the conclusion. So I'm going to conclude that it is not safe to go outside. And that's my answer. So not too complicated, but that's the general gist of the law of detachment. Let's look at one more example.
Okay. Do you have any question?
No.
Yeah, I think it's clear, right? So the law of detachment says if the hypothesis are true, conditional statement is true, then the conclusion is true. So if P then Q true, and then P true, so the Q is true. Okay. So something like this one. If there's a lightning, then it is not safe to go outside. And Johnny sees lightning out his window. So the conclusion is it's not
Is
safe to
P
go
and
outside.
Q?
Yeah.
Is P and Q, is that the only like letters to use, or was that just an example?
Yeah, I think most of the people using P and Q.
Okay.
Yeah, so we just follow the common people. I mean the common.
So that's the equation. Like that's how you set it up.
Yes.
Okay.
So we use the letter P and Q for all of the logic, symbolic logic. Okay, so the next example is this one.
So here it says, if a figure is a square, then its sides are all congruent. Figure ABCD has all congruent sides. So what can we conclude? Now a lot of students think that, oh, you can conclude that it's a square, but we have to be really careful with the law of detachment. Here, my hypothesis is that the figure has to be a square. My conclusion is that its sides are all congruent. So here I have P then Q, and then my additional piece of information that I need says that it has all congruent sides. If we look, that piece of information actually matches Q. It's saying that Q is true. And even though a lot of us might really want to conclude then that P has to be true, unfortunately, the law of detachment doesn't work that way. We can only go the direction that it states. We have to be given the hypothesis and then conclude the conclusion. So here, I have no conclusion. I can't conclude anything. And let me kind of give you a little example or counterexample why we can't conclude that ABCD is a square. So counterexample, if I have ABCD with all congruent sides, it doesn't have to be a square. It could be what we call a rhombus. So just because the conclusion that it has all congruent sides was true, it doesn't mean that it has to be a square. So be really careful. Make sure that the ordering goes exactly as the law of detachment states. All right, last piece of information, we have the law of syllogism. That states that you can take two conditional statements and string them together if the conclusion of the first one is the hypothesis of the second one. So symbolically, what I have is I would have P then Q, and then I would have Q then R. So I have three pieces of information here that are totally separate, but the conclusion of the first one ends up being the hypothesis of the second. If I have those specific orderings, I can conclude the statement P then R. So I can take out the middle guy, I can take out the Q. So let's look at an example. If it is raining, Susie will stay inside. If Susie stays inside, she will play board games. So here we have three pieces of information. We have it is raining, let's make that our P. We have Susie will stay inside, we'll make that Q. And then Susie stays inside is repeated. Remember, that's Q, so it's not a new piece of information, it's the same. And then she will play board games is our third piece of information here. So I have if it is raining, Susie will stay inside. I have P then Q. Then I have if Susie stays inside, she will play board games, which is Q then R. This fits our law of syllogism. So my conclusion should be a conditional statement, P then R. Now notice if we were using the law of detachment in the last example, our conclusion was not a conditional statement. If we look back, it is not safe to go outside is not an if-then statement. It's just the conclusion part. But for the law of syllogism, we want our conclusion, or what we want to conclude from these statements, to be a complete conditional statement. So I need to say P, which is if it is raining, and then I can take out the Q's. I can take out those middle pieces, and I would say she will play board games, but I want to say who she is because it's not stated yet. So I'm going to say Susie will play board games. And that's what we can conclude using the law of syllogism. All right, and that concludes our lesson for today. Thank you for watching.
Okay, so do you have any question?
No.
Yeah, so
No.
for question number 3, right? Because question number 3 related to the related to the lesson 3, right? So lesson 3 about 3 things, right? First is deductive reasoning. So what is deductive reasoning? And then the second one is about the law of detachment. So you need to answer this one and explain what is law of detachment, what is inductive reasoning, sorry, and then what is the syllogism. So the last one is talking about the law of syllogism. Yeah, law of detachment and law of syllogism. So you have to explain this law of syllogism, and this is the example. Okay, I think we can continue with the lesson. So any question? If you don't have any question, you can continue with the lesson 4, right?
No questions.
Okay, go ahead.
I said no questions.
Oh, no question? Okay, I thought you have question. Okay. Okay, so so the next question will be lesson 4, right? Okay. So we need to check the lesson 4.
Hi class, welcome to Math is Fun, Demental. Today we're going to introduce proofs. Now this is something totally new, probably never seen before, so this will just be a little lesson to jump into proofs in geometry. So let's get started with some properties of equality. Now these may seem a little familiar to you, which is good. We have the addition property, which states if A equals B, then A plus C equals B plus C. All that means is if I have some sort of statement like if X equals 5, then I can take a number or a variable and add it to both sides of an equation. So I can say that X plus 2 equals 5 plus 2. So I'm just taking something and adding it to both sides of our equation. Subtraction property, same idea, but this time instead of adding, we'll be subtracting. So if X equals 5, then X minus 2 equals 5 minus 2. So just taking that 2 and subtracting it from both sides of the equation. Multiplication property, moving through here, if X equals 5, then 2X equals 2 times 5. Division property, if A equals B and C isn't 0, then A over C equals B over C, or A divided by C equals B divided.
Okay, well, because of the time, okay, let me skip it. Okay. So you can see here.
And then use that to solve for y. All right, so a very, very common confusion is the difference between transitive and symmetric, or sorry, transitive and substitution. So I just want to kind of talk about it a little tiny bit. Transitive property is a type of substitution. So I'm going to draw a little diagram here. So if substitution is this large area, transitive property is a subset of substitution. Transitive. So it's a type of substitution, which means if transitive property applies in your proof, then technically substitution will always work wherever transitive works, but it doesn't always go the other direction. In the example that we put in our table for substitution, transitive property would not have worked for that. So be a little bit careful. I like to use transitive if it's really all equals or all congruent signs connecting all the pieces. Transitive is fun. But if it's not all equals, for example, in that substitution property example where I had x plus y and then x equals 30 and I'm substituting that in, transitive would not apply. So be really careful about the two of those. All right, some properties of congruence. So we had properties of equality, now we have properties of congruence. Reflexive property of congruence, again, is going to be something like segment AB is congruent to segment AB. Reflexive property, think of it like a reflection in a mirror. You're looking straight at yourself, so both sides of those congruent signs or equal signs are going to be the same. All right, symmetric property of congruence. These properties are going to be the same as the properties of equality, except we have congruent signs now. So if I have, if x is congruent to, well, let's make these geometrically. Okay, let's say a.
Yeah, so there are two properties, property of equality, and then the one is a property of congruence. Okay. So for the property of equality, there are property is 1, 2, 3, 4, 5, 6, 7, 8. Okay. And for the congruent property, we only have 1, 2, 3, 4. Okay. Oh no, I think you have more. Yes, sir. So you have more. Yeah. Okay. So 1, 2, 3, 4. No, I think it's 4. Sorry, sorry. Yeah, I think it's 4. Okay. So you have reflective, symmetric, transitive, and substitution property. Only 4. Okay. Sorry. And this is the statement of what proof. Proof is a series of statements that, yeah, for example, like if you want to prove this, so you have to use this step here.
Just a simple algebra problem solving for x and a proof when you're solving for x or proving something. So let's look at an example. And proofs are going to take some practice, but you'll get them. All right, if the measure of angle 1 is 5x plus 7 degrees, the measure of angle 2 is 3x plus 11 degrees, and we're given that the measure of angle 1 equals the measure of angle 2, then what is the value of x? So it seems like a simple little algebra problem for us, but I want to talk about what a proof is. So we're going to justify every single step just to kind of get into what a proof really is. So first thing we're going to do is start with the given information. So here I'm going to have the measure of angle 1 equals 5x plus 7 degrees, and the measure of angle 2 equals 3x plus 11 degrees. So we'll call this step 1. And we're just going to write the word given because it was given to us in our information for the problem. Now, we're given another piece of information. We're given that the measure of angle 1 equals the measure of angle 2. So I'm going to put that next, and I'm going to put given again. It's a different statement. We can combine. We could have put all three of those in our line 1, but we can also separate them. Proofs give you a little wiggle room to make it your own. All right, now the third step, here's where we want to start doing things to solve for that x. So if I know that the measure of angle 1 is 5x plus 7 and the measure of angle 2 is 3x plus 11, I can take 5x plus 7 and replace measure of angle 1 with that amount. So 5x plus 7 equals, and then I can do the same for measure of angle 2. Instead of the measure of angle 2, I can replace it with 3x plus 11. Now here, we could actually either use, because it's all equalities, we could use transitive property of equality, or we could use substitution property of equality. I'm going to use substitution in this case because I kind of did two different steps in one. I substituted 5x plus 7 in for measure of angle 1, and I substituted 3x plus 11 in for measure of angle 2. So with a couple steps at the same time, I think substitution is a little safer, but again, transitive property would also work here. Substitution property of equality. So we want to write property of equality, and we can symbolize that a little. All right, now let's solve this like an algebra problem, but we need to use our properties to justify our work. So here, I want to subtract 3x, and we can do the work, but we don't want to count it as a step. So you can do this, and we want to do one step at a time. So my next line of my proof would be 2x plus 7 equals 11. So it's not the actual negative 3x on both sides or subtracting 3x on both sides. That's my line in my proof. But we can show that for our own sake if we want. So here we want to think, okay, how did I get from 3 to 4? Well, I subtracted 3x from both sides. Subtracting something on both sides is our subtraction property of equality. So that's how I would justify that step. All right, next step, we're going to do kind of the same thing. I'm going to subtract 7 on both sides. So I end up with 2x equals 4. So on step 5, again, I'm going to get subtraction property of equality. And my last step, if I take and divide both sides by 2, I get that x equals 2. And again, I divided something from both sides, so that's going to be my division property of equality. And that's the end of our proof. Now, if you want to be really fancy, to symbolize that it's the end of a proof, you can put a little box and color it in like that. There's a couple other ways you could do that, but it's just a nice little symbol that states, okay, I'm done with my proof now. So that's a little bit of an introduction for you into proofs. And that concludes our lesson for today. So thanks for watching, and remember, math is fundamental.
Okay, so yeah, this is will be the lesson for today, right? So lesson 3 and 4. Okay. So you let's remember there are two property here. The one is equality property. Right? We have 1, 2, 3, 4, 5, 6, 7, 8. We have to explain all this. I need to give you the example. And then the second property is call it congruent property. There are 4 congruent criteria. This is the rule, and then you can find what is the example. And the third one is talking about the proof. Right? How to use the proof using the property. But in this example here, the proof is using the property of equality. You can see here. Okay. So any question?
No.
So everyone understand about this?